Welcome to the video help with physics problems for Physics 1A. In this video we're going to cover homework set 3, part 3. This is everything under the headings, rotational kinematics and revision. So for 1121 students this covers questions 10 to 14. For 1131 students this covers questions 13 to 19. This is problem 10 for 1121 or 13 for 1131. Now we're told that the Earth, which is rotating, has tidal forces acting on it, and this causes the period of rotation to increase by 2.5 times 10 to the minus 8 seconds per day. Okay, so let's write this down. The change, D represents change in the period with time, is equal to 2.5 times 10 to the minus 8 seconds per day. Now, these aren't very useful units. The per day is not good. So let's get this, how much is the period changing per second? So this is equal to 2.5 times 10 to the minus 8 seconds. And then to convert it from per day to per second, we'll have to divide it by the number of hours in the day, the number of minutes in an hour, and the number of seconds in a minute. So this will give us seconds per second instead of per day, and this is equal to 2.89 times 10 to the minus 13 when we do that on the calculator. Now, part A of the question asks us, what is the angular acceleration? Well, we know that the angular speed, omega, is equal to 2 pi over t. And we also know that alpha, the angular acceleration, is equal to d omega dt, the derivative of omega with time. So we can use the chain rule. This is d omega dt, where t is the period, dt, t is the period, t is an increment of time. And so doing this, d omega dt, taking the derivative of this, we get minus 2 pi over t squared. Because remember, this is just 2 pi t to the minus 1, so we bring the minus 1 out the front, make it minus 2, which makes a t squared on the bottom, and we keep our constant. And then this is times dt dt. Now we do have a value for the rate of change of the period just here. So now we just need to substitute everything in, and this will be in radians per second per second. Okay, so substituting in. Before we can substitute in the period, we should actually calculate it. We know that the period for Earth's orbit is 24 hours. So it's 24 hours times 60 times 60 seconds. Solving this on the calculator, we get 86,400 seconds. Okay, now we're ready to substitute everything in. So this is minus 2 pi over 86,400 squared times 2.89 times 10 to the minus 13. Solving that on the calculator, we get minus 2.43 times 10 to the minus 22 radians per second per second. And then we should give everything to two significant figures, as this was two significant figures. So this is minus 2.4 times 10 to the minus 22 radians per second per second. Okay, part B, what would be the Earth's period be in a billion years' time, assuming that alpha remains constant? Let's make ourselves some room here. We know that the rate of change of the period is equal to 2.89 times 10 to the minus 13 times the length of time that we're considering. So all we need to do is substitute in here the length of time. This time it's not a little increment of time, it's a very big one. It's 10 to the 9 years. So this is, we need it in seconds, so it's 2.89 times 10 to the minus 13. Well, if we put it in seconds, then our dt will be in seconds. So let's do it in seconds for now and see if that works out well for us. So it's 10 to the 9 years, which is times 365 gets it into days, times 24 gets it into hours, into minutes, and into seconds. So entering all this on the calculator, we get 9,113 seconds. It's a lot of seconds. So if we divide it by 60, we get it back into minutes, and then divide it by 60 again to get it into hours, we end up with 2.5 hours. So that's the change in the period over 10 to the 9 years. But what the question actually asked us for is what would be Earth's period. So the period is equal to the initial period plus the change in the period. So the initial period is the 24 hours, plus we've got the change in the period, which is 2.5. So this gives us 26.5 hours is the period of the Earth's orbit in 10 to the 9 years. So a very long way into the future. Problem 11 for 1121 or 14 for 1131. Okay, we're assuming that the Earth is a sphere with uniform density throughout it. Okay, so sphere, it's got some radius and it's rotating. Part A asks us, what is the rotational kinetic energy? Okay, so the kinetic energy due to rotation, the formula for that is a half I omega squared. So we need to work out the moment of inertia and the angular speed of the Earth. Okay, now the Earth's a sphere, so the moment of inertia of a sphere is given by 2/5 mr squared, which is equal to 2/5. The mass of the Earth is 6.0 times 10 to the 24 kilograms times the radius squared, which is 6.4 times 10 to the 3 kilometers. So putting that in meters. Okay, so solving this on the calculator, we get 9.83 times 10 to the 37 is the moment of inertia. So what's that? Kilogram meters squared. Okay, so we've calculated the moment of inertia. Now we need to calculate omega. So omega is equal to 2 pi on t. T is the period of rotation of the Earth, so that's 2 pi. We need it in seconds, so it's 24 hours times 60 minutes times 60 seconds. Solving this on the calculator, we end up with 7.27 times 10 to the minus 5 radians per second. Okay, now we can substitute everything into this equation. So the kinetic energy of rotation is a half times 9.83 times 10 to the 37 times 7.27 times 10 to the minus 5 squared. Solving that on the calculator gives us 2.5977 times 10 to the 29, which to two significant figures is 2.6 times 10 to the 29 joules. Okay, part B says, suppose this energy could be harnessed for people's use. For how long could the Earth supply 1 kilowatt hour of power to each of the 10 to the 10 people on Earth? Okay, so the time it could supply for is given by the total energy over the rate of energy use. So this is 2.6 times 10 to the 29 divided by the rate of energy use. So we're told that there are approximately 10 to the 10 people on Earth and that they are using 1 kilowatt. So that's 1,000 watts. Okay, so entering this into the calculator, we get 2.5978 times 10 to the 16 seconds. Seconds isn't very useful. Let's get that into years. So to get it into years, we divide it by 365 days, 24 hours, 60 minutes, 60 seconds. Solving that on the calculator, we get 8.2 times 10 to the 8 years. Now this was only a very approximate number, so we shouldn't really give the number this precisely. So we can say that this is around about 10 to the 9 years. Problem 15, which is a 1131 only problem. In this problem, we've got an inclined plane. It's inclined at an angle theta is equal to 30 degrees. We've got a pulley here, and this pulley we're not told is weightless. It's actually got a mass equal to m, and it's got a radius is equal to 0.1 meters. So we can't ignore this pulley as we usually do. We've got a hanging mass here, m1, which has mass 9 kilograms. And there'll be a tension force here acting upwards, pulling that up. And we've got another mass, m2, which is 3 kilograms. On this plane, it has a force T2 upwards. There is a frictional force acting against this, and the coefficient of kinetic friction is equal to 0.10. In this question, we're asked to find the acceleration of the blocks and also T1 and T2, the tension between the pulley in mass 1 and the pulley in mass 2. So this question's more complicated than what we've seen before, but we go about it in exactly the same way. So we use Newton's second law to write down the expression for the total forces and acceleration acting on each of these blocks. So let's consider block 1. We've got m1a is equal to, the big force acting on it pulling it down is m1g, and then there's T1 pulling it up. Those are the only two forces acting on this block. Let's call that equation 1. Okay, now let's consider block 2 here. Now to do this, we've got m2g acting downwards. And remember, we have to consider the component of the weight force parallel to the plane and perpendicular to the plane. So this is 30 degrees here. So this is m2g sine 30. That's the weight force pulling it down the plane. And then m2g cos 30. That's the weight force pushing it down into the plane. So we have the normal reaction force, which has the same magnitude as this. So that will tell us that our frictional force will be equal to mu k m2g cos 30. Okay, so let's write down our expression for this second block. The total forces acting on block 2 are, we've got T2, which is the biggest force, pulling it up the plane. Then we've got the friction force pulling it down, which we said was given by mu k m2g cos 30. And then we've got the weight force also pulling it down the plane, which is this minus m2g sine 30. Now we've got two equations there, but three unknowns. We don't know A, we don't know T1, and we don't know T2. So we need another equation as well. We can write an equation for this pulley here. Torque is given by R cross F, and it's also equal to I alpha. So for this pulley, the distance from the pivot point is just the radius. The force is got T1 acting in this direction and T2 acting in this direction. So the force is the difference between those. We've got T1 minus T2. And the moment of inertia for a disc, which is what a pulley is given by a half mr squared. And alpha can be written as the acceleration over radius. So the angular acceleration is equal to the linear acceleration of the radius. So let's substitute in here. We have r, T1 minus T2 is equal to a half mr squared times a over r. Let's get T1 and T2 together. So T1 minus T2. Now when we divide by the r, we're dividing by r squared. So these will actually all cancel. And we'll have this is equal to a half ma. So let's call that equation 3. Okay, so now we've got three simultaneous equations and three unknowns. So we can solve these to work out A, T1 and T2. So if we do 1 plus 2 plus 3, we'll add this to this side. So we've got the acceleration, we've got m1 plus m2 plus a half m, capital M. And now this T1 will cancel that T1, so we're left with just m1g on this side, and this T2 will cancel this minus T2. So we've got minus mu k m2g cos 30 minus m2g sine 30. And so solving for the acceleration, we just divide by this. We can substitute in all our numbers. We've got 9 times 9.8 minus 0.1 times 3 times 9.8 cos 30 minus 3 times 9.8 times sine 30 over m1 plus m2 plus a half m, so 9 plus 3 plus half times 1 is 0.5. Solving that on the calculator, we end up with 70.953 over 12.5, which gives us 5.67, or just to two significant figures, 5.7 meters per second as the acceleration. So now we found A, we've also been asked to find T1 and T2. So to solve T1, let's substitute into equation 1. We've got T1 is equal to m1 g minus a, so that's 9 times 9.8 minus 5.7. Solving that on the calculator, we end up with 37 newtons. Okay, to solve T2, it's easiest to use equation 3. So T2 is equal to T1 minus a half ma. T1's 37, m is 1, and a is 5.7. So substituting that into the calculator, we end up with 34 newtons. So that's the answer to this problem. Problem 12 for 1121, or problem 16 for 1131. In this problem, we've got an inclined plane. It's at an angle theta, and it's got a height h. And we've got a uniform sphere up here. It's got radius r, mass m, and it's rolling down the plane. As it's rolling, if we need to consider friction, we'll be using mu s rather than mu k. And we're told that at some point as it's traveling down the plane, it's got the velocity of its center of mass is given by v. Okay, part A for this question asks us to derive an expression for the total kinetic energy. Now, the total kinetic energy in this case comes about from two parts: the rotational kinetic energy and the translational kinetic energy. So the translational kinetic energy is just the kinetic energy due to the movement of the center of mass, so that's capital M V squared, and the rotational kinetic energy is given by a half I omega squared. Now this is a sphere, so we've got I is equal to 2/5 mr squared, and we know that V is equal to omega r, which tells us that omega is equal to V on r. Okay, so we can substitute this in here. We've got a half mv squared plus a half times 2/5, 2's will cancel, mr squared, and then omega squared, so this is V on r squared. Okay, so we've got a half mv squared. This r squared will cancel with this r squared, and we'll actually end up with a 1/5 mv squared. Okay, so just adding these together, let's put them over 10. We've got 5/10 mv squared plus 2/10 mv squared, so that's 7/10 mv squared. So that's the total kinetic energy. Okay, part B, it asks us what is the angular velocity of the sphere when it reaches the bottom of the inclined plane. So we need to find omega. Okay, well, if we find V, then we can find omega. So at the bottom of the inclined plane, all the gravitational potential energy it had up here has been converted into kinetic energy. And so we have mgh is equal to 7/10 mv squared. cancel the m's, and we end up with v squared is equal to 10 over 7 times gh. What we're asked for is this angular velocity, so we'll need to find v. So v is equal to root 10 on 7 gh, and so omega is equal to root 10 on 7 gh over r. Part C, we're asked to find the magnitude of the linear acceleration down here. We've got its final velocity here, so we can use v squared is equal to v naught squared plus 2ax, where x is the distance travelled. So we need to work out what this x is. We know that h is equal to x sine theta, and so x is equal to h over sine theta. That's the distance it's travelled down the slope. The initial velocity was 0. So we've got 10 over 7 gh, that's v squared, is equal to 2a times h over sine theta. So a is equal to 10 over 7 gh times sine theta over 2h. Okay, let's simplify. The h's will cancel out, this 2 will cancel and give us a 5, and so this is 5 on 7 g sine theta. Okay, part D, it asks us how long does it take to roll down the plane given that it starts from rest. So let's use x is equal to ut, which is 0, plus a half at squared. We've got the acceleration now, and so t squared is equal to 2x over a. So x is 2h over sine theta on a, so this is on 5, 7 g sine theta. And so this is equal to 14 on 5 h over g sine squared theta is equal to t squared. So t is equal to the square root of that. And that's the answer to that problem. Problem 17. This is 1131 only. In this problem, we have a rod which is pivoted about a point. So here's our rod. It makes an angle theta, so it oscillates backwards and forwards, making an angle theta. The length of the rod is L. The rod's of uniform density, so the center of mass is in the middle of the rod. So this is L on 2, L on 2, and we're told that the distance from the pivot point to the center of mass is given by x. The mass of the rod is m, and the total length is L. So part A asks, what is the torque acting on the pendulum when its angular displacement from the vertical is theta? Okay, now there's two ways to do this, the easy way and the hard way. The easy way is to say that this is equivalent to having all the mass at the center of mass, so at this point here. So if we do that, then torque is equal to R cross F, and so the distance from the center of mass, which is what this R is X. F, we've got all the mass concentrated here, so the force there is mg, and then because of the cross product, the angle between R and F, theta, so we end up with sine theta. Okay, so that's the easy way. The hard way is to consider each little component of mass on this rod. So let's break this rod up into little components with length dl and mass dm is equal to the mass density, which is the total mass over the length, times the length of that increment. So let's define little l as the distance from the pivot point. Now the bits up above the pivot point will cancel out an equal length for the bits below the pivot point, because this rod is of uniform density, and torque, the direction up above, is R cross F, so that's coming up out of the page, and this is going down into the page, so this part and that part will cancel each other out. So to get the torque, in this case we have to add up. Now we want to add up from here to here. So L is the distance from this point here. So this distance is L on 2 minus X, and as you can see, the distance from here to here is given by L on 2 plus X. So this is L on 2 plus X. So we're adding up from L on 2 minus X to L on 2 plus X. So that's everything in this region here. Now the distance of each of these little increments of mass from the pivot point is given by L. That's how we defined it. The force on each of those increments is given by M on L G dl, and then because of this cross product we still have a sine theta. Okay, so now we have to do this integral, so we can pull all the constants out the front. We've got M on L G, and now when we do the integral it's L dl, so that's L squared on 2 from L on 2 plus X to L on 2 minus X, and then we've got our sine theta, which could go out the front here. Okay, so let's write this as M over 2L G sine theta. And now putting this into here, we've got L on 2 plus X all squared, so that's L squared on 4 plus LX plus X squared, and then we have to subtract off this, so that's minus L squared on 4. And then minus minus, so that's plus L on X, and then minus X squared is X squared, so minus that, that's minus X squared. Okay, so this cancels that, that cancels that, and we end up with mg sine theta on 2L times 2LX, 2's cancel, L's cancel, and we end up with mg x sine theta, which is the same as up here, but it took a lot more working to get there. Okay, now we're on to part B. We need some more space, but we've got this same diagram that we're considering here with the center of mass at distance x from the pivot point, and this having total length L. Okay, so part B says show that the rotational inertia is given by this expression. Okay, so to do this we're going to have to use the central axis theorem, which tells us that I is equal to the moment of inertia about the center of mass plus md squared, where d is given as the distance between pivot and the center of mass. So in our case this is x. That's how we defined x. So this term will just be mx squared. So let's work out what the moment of inertia is about the center of mass. So we've got a rod here. The center of mass is right in the middle. So this is minus L on 2, 0, L on 2. I is equal to r squared dm. Now each little increment here has mass dm, which is equal to m over L times dl, the length of the increment. Okay, so let's calculate the moment of inertia. To do that we're going to need to add up all the increments along the rod. So we've got from minus L onto to L onto R squared, so that's L squared, L's the distance from the centre of mass, times dm, which is m over L dl. Okay, so this is m over L out the front. Now when we integrate, we've got L squared dl, so that's L cubed on 3 from L on 2 to minus L on 2. So this is equal to m over 3L, we're pulling this 3 out the front. Then this is L cubed over 8 minus, so that's plus L cubed over 8. Okay, so this in here is L cubed on 4. So this is m over 3L, L cubed on 4. This will cancel and we'll end up with ml squared over 12. Okay, so that's the I centre of mass. So now I can substitute everything in here and we have I is equal to ml squared on 12 plus mx squared. Part C. In this part we're asked to assume that theta is small and to derive an expression for the period in terms of x and L. So at the beginning we derived an expression for the torque. We got torque is equal to mg x sine theta, and that torque was directed into the page, so let's give it a negative sign. Now we're making the small angle approximation, so sine theta is approximately theta, so the torque is approximately mg x theta. Now Newton's second law for rotation tells us that the torque is also equal to the moment of inertia times alpha, and we derived an expression for the moment of inertia in part B. So alpha is equal to minus mgx theta over I, where I is given by mx squared plus L squared over 12. Okay, cancel the m's and we have alpha is equal to minus gx theta over x squared plus L squared over 12. Okay. Now we need to be a bit tricky to get this into a form for t. What we need to do is realise that this is a pendulum, so it's undergoing simple harmonic motion. So theta, the angle, is going to have the form theta naught is equal to sine omega t plus phi, the phase constant. D theta dt is then equal to minus theta naught omega cos omega t plus phi, just taking the derivative of this, that's omega, and alpha is equal to d squared theta dt squared, which is equal to minus theta naught omega squared sine omega t plus phi, which is equal to minus omega squared times theta, because this thing here with the theta naught is a theta. Okay, so this is equal to minus omega squared theta, and so we have omega is equal to gx over x squared plus L squared on 12 to the 1/2. And omega is defined as 2 pi on t. So rearranging this, we end up with t is equal to 2 pi times x squared plus L squared over 12 all over gx to the 1/2. And that's our expression for the period in terms of x and L. Part D, now we're asked to find the minimum value of x, well, the value of x for which t is a minimum. So we derive the expression for t, that t is equal to 2 pi x squared plus L squared over 12 over gx to the 1/2. Okay, now if t is a minimum, t squared will also be a minimum. So let's just write this as t squared over 4 pi squared is equal to x squared plus L squared over 12 gx. Okay, now if t is minimum, t squared over 4 pi squared will also be a minimum. And this is a much simpler expression to find the minimum of. So dt squared over 4 pi squared dx, we want to find the minimum with respect to x, so we need to differentiate it. Okay, this is, let's just rewrite this. This is x on g plus L squared over 12gx. So now we take the derivative of this with respect to x, so we end up with 1 on g plus minus, L squared over 12gx squared. For a minimum, we set this equals to 0. So those g's will actually cancel out, and we'll have 1 is equal to L squared over 12x squared, giving us x squared is equal to L squared on 12, or x is equal to L over root 12. So we found our minimum x there. Okay, part E says L is equal to 1.0 meters, and you need to find the minimum period t and the minimum value of x. Okay, so the minimum value of x is given by this. So x is equal to 1 on root 12. Solving that on the calculator, we end up with 0.2886, which is equal to 0.29 meters to two significant figures. Okay, now we need to substitute all of this back into here to get our minimum period. So this is 2 pi times x squared, so 0.2886 squared, plus L squared, which is 1 on 12, over 9.8 times 0.2886, or to the 1/2. Enter that into the calculator, and we end up with 1.53, which is equal to 1.5 seconds to two significant figures. So that's the end of this question. Okay, we're up to the revision. This is question 13 for 1121 or 18 for 1131. We're told that a particle follows the trajectory given by 3ti plus 1 plus t squared in the j direction, and that this particle has a mass equal to 2 kilograms. In part A of the question, we're asked to sketch a trajectory for this particle. So we need to find out the relationship between the x components and the y components. So the x component is given by 3t, so we can write this as t is equal to x on 3. The y component is given by 1 plus t squared. So if we substitute in for t here, we'll get a relationship between y and x. So this is 1 plus x squared on 9. Okay, so let's sketch this trajectory. Here's our x component, here's our y component. When x is 0, y is 1. And then it just increases like a parabola. So this is our trajectory here. Now part B says calculate the velocity and acceleration of the particle. The velocity is given by dr dt. So we need to take the derivative of this function with time. So in the I direction, 3t, take the derivative, we get 3i. In the j direction, we need to take the derivative of 1 plus t squared, which is just 2t in the j direction. So that's meters per second. For the acceleration, we take the derivative of the velocity, or the double derivative of the position. So the derivative of 3i is 0. The derivative of 2t is 2j. And that's meters per second per second. Part C says determine the force acting on the particle. Just use Newton's second law. F is equal to ma. M we're told is 2. So this is equal to 4j newtons. Part D says calculate the vector torque and angular momentum of the particle about the origin. Okay, torque is given by R cross F. Sorry, that's not the unit vector, it's the radial vector. So to do this, to find the cross product, we can find the determinant of the matrix. R is given up here, so it's 3t in the I direction, 1 plus t squared in the j direction, no k component. F, we're told we calculated was 4j, so that's 0, 0. Finding the determinant of this matrix, it's got nothing in the I direction, it's got nothing in the j direction. In the k direction, it's 3t times 4, so that's equal to 12tk. Okay, and then we're asked to find the angular momentum as well. Now, angular momentum is equal to r cross p, the momentum, and the momentum is given by mv. Okay, so find the determinant of the matrix. R is the same, so that's 3t, 1 plus t squared, 0. mv, v is over here, so we need to multiply that by 2. So that is 6 in the I direction, 2 times 2t is 4t in the j direction, and nothing in the k direction. Finding the determinant, I component 0, j component 0. In the k component, we've got 3t times 4t, so that's 12t squared, minus 6 times 1 plus t squared. This is in the k direction. So this is 12t squared minus 6t squared, so that's 6t squared minus 6. Okay. Okay, so that's the answer to part D. To part E, it says, show that your result in D satisfies that the torque is equal to dl dt. Okay, let's calculate dl dt. We need to take the derivative of this with time. So the derivative of this is 12t. The derivative of 6 is 0, and this is in the k direction. This is equal to this, so this is equal to the torque. So we've shown that dl dt is equal to the torque in this case. Okay, the final problem in this set, problem 14 for 1121, which is problem 19 for 1131. Now we have an alpha particle. It's travelling along and it collides with a stationary oxygen nucleus. The alpha particle is scattered at an angle of 64 degrees to the direction of its original velocity. So this is the alpha particle, this is 64 degrees. This is the momentum of the alpha particle. And the oxygen nucleus recoils at an angle 51 degrees on the other side of the initial direction. Okay, so down here, 51 degrees. This is the momentum of the oxygen atom nucleus. So here's the oxygen nucleus going down here. The question is asking us to find the ratio of the speed of the alpha particle to the oxygen nucleus. In this question, we can consider the vertical components. If we consider that the alpha particle was initially traveling just in a horizontal direction, and we know that the momentum, because of conservation of momentum in these two directions, must be equal but opposite. So the momentum up here is given by P alpha sine 64, and here by P, the momentum of the oxygen atom, times sine 51. So we know that these two components must be equal in magnitude. So P alpha sine 64 is equal to P oxygen sine 51. Okay, so rearranging, we have P alpha over P oxygen is equal to sine 51 over sine 64. And we can rewrite this. The momentum is given by M alpha, V alpha, and the momentum for the oxygen nucleus is mass of oxygen, V of oxygen. And we're told in the question that the oxygen nucleus is 4 times the mass of the alpha nucleus. So we have M alpha V alpha over 4M alpha VO. Those will cancel. And so we end up with V alpha over V oxygen. This is for the oxygen nucleus, is equal to 4 times sine 51 over sine 64. So we just need to type this expression into the calculator. When we do that, we end up with 3.46. So these angles were two significant figures, so let's give that as 3.5 for our ratio. As it's a ratio, it doesn't have units. And that's the answer.